wanted to rebuild our configuration management system at Facebook. Um, and before I get into that, I want to talk a little bit, I want to give you one slide. My pet peeve at conferences is people who stand up on stage in front of a crowd full of people and then don't give me an idea of why I should listen to them. So I'm going to give you one slide on why I think I'm qualified to talk about this. And if you don't agree, there's two other awesome talks going on. At the end of the next slide, if you want to leave, you can go to that and I won't be offended. So I have a lot of configuration management experience. In addition to using most of the configuration management systems that exist out there, I also helped write one at Ticketmaster. Back in the days before Puppet and Chef, we needed something that was better than CF Engine 2, and we wrote something called Spine, which you can find on GitHub today. And after Spine worked, we needed something that was going to enable us to build systems that could then run Spine. So I wrote Provision, which would do things like allocate VMs and DNS. I've been working at scale for a while. As I said, I was at Ticketmaster, which had about 6,000 systems when I left, and then Google, which has systems, and Facebook, which has a lot of systems, and I'll talk a little bit about that as we go along. But ultimately, my passion has been scaling configuration management for the almost 15 years that I've been working in this industry. So let's talk a little bit about scale. If you're going to build a configuration management system that you need to scale, the first thing you need to do is actually understand what kind of scale you need. And there are many different kinds of scale, and every environment has different requirements. And in order to figure that out, you need to ask yourself a few questions. One question you probably need to ask yourself is, how many homogeneous systems can I maintain? And if this describes your environment, you have a unique set of requirements and may be able to use something as simple as rdist or rsync, or the IBM XCAT tools, which are excellent for this sort of thing. But even if this doesn't describe your environment, even if you have a hugely heterogeneous environment, ultimately heterogeneous environments are usually made up of groups of homogeneous environments. And so it's still a useful thing to understand and ask yourself. But more to the point for most people in this room, how many heterogeneous systems can you maintain? Most of you have a large app that you're trying to manage, and so it has web servers and cache servers and database servers and whatever else. And so this is ultimately the question that most of you guys are going to be getting at. And you also need to ask yourself how many people are going to be needed to maintain this environment, because I'm pretty sure no one wants to throw one admin per server. That does not work very well. And then finally, the question that I think gets overlooked more often than it should is, can I delegate Delta configuration? Can I take the little changes that people want to make and let them make them? And we'll talk about why I believe this leads very directly to scale as the talk goes on. Once you've asked yourselves these questions, you need to figure out what your goal is. What's your goal in managing your infrastructure? And everyone's going to have a slightly different one, but at Facebook, our goal was pretty simple. We wanted 4 people to be able to manage hundreds of thousands of heterogeneous systems. And we wanted service owners to be able to own and change their own relevant settings. And by service owners here, I mean software engineers and production engineers that own some specific set of the environment. It's very common at Facebook for software engineers to manage a system for a long time until it becomes mature enough to warrant what we call production engineering support. So with the goal in mind, we sat down and tried to draw out what our needs were going to be. And while your goal is probably different from our goal, I argue that most of these needs will actually come in handy for whatever your goal may be. And the first goal is basic scalable building blocks. What are those pieces that you want in a piece of software that you're going to pick that's going to enable you to scale it on a variety of axes for your needs? And the first one of those is distributed. Everything has to run on the client that possibly can. It turns out that if you have a system that's not distributed, if your configuration management is bottlenecking things on some central resource, then when you want to scale your application, say make more web servers or make more cache servers or database servers, you have to stop and think, well, is my configuration management system going to support this extra load? And so by scaling one system to solve one problem, you immediately end up with yet another scalability problem. And I don't like scalability problems that lead to other scalability problems. Alternatively, imagine where everything runs on the client, so as you make more web servers, as you make more cache servers or whatever, you inherently scale your configuration management system. Scaling one thing scales all things. It's a much better way to do it. We wanted it to be deterministic. Eventual consistency is not something that works in this realm, right? When I run my configuration management system and it exits successfully, I need to know that the system I have is one that is ready for production. I don't want to have to run it 2 or 3 or 5 or 10 times just in case. That's not okay. It's got to be idempotent. So in other words, I want to be able to run it again and again and have it only make the changes that are necessary. If the system is perfectly configured and I run my configuration management system, don't make any changes. It's got to be extensible. At Facebook, as a large company, obviously we have internal systems, but every company out there has some internal system. Every .com I worked for had a CSV file, access database, a SQLite file, something that constitutes an internal system that tracks something. And your ability to tie into whatever your system is will enable you to grow and scale faster. And finally, it needed to be flexible. Obviously, again, Facebook as a big company has a unique workflow. We push code twice a day. We push configs every 15 minutes. But you all have a workflow as well that has enabled your business to be successful, that has enabled your development teams to do what they need to do. And so when you pick a tool, you don't want to pick a tool that's going to make you have to bend your workflow to the tool. You want a tool that's going to bend to your workflow. The second thing we needed was configuration as data. And this is sort of a fuzzy concept, so I'm going to try and define it. Let's say you're a service owner. You know a variety of things. You may know that you need more shared memory, or that you would like to be able to answer requests on an additional IP address or interface, or that you need a service running more or less and a CD caching, whatever it is. But as a service owner, what you may not know is how do I configure that additional VIP? Or what are all the other network settings? Or just because I moved core files, which happens to exist in syscontrol, do I necessarily know every other value for every other syscontrol in the box? Probably not. So what we wanted was a system where you could represent these things that you wanted as simple data structures, arrays and hashes. Represent the couple of syscontrols you care about as a hash. Represent the extra IP addresses you needed as an array. And then pass that into a larger system that merges it into the larger set of data and uses that set of data to configure the system. The third thing we needed was flexibility, and I touched on this a little bit when I said we wanted something that adapted to our workflow. But there's other things that come under the umbrella of flexibility. We wanted super fast prototyping. It turns out that at Facebook, obviously, well, let me start over. Everyone's heard that old story about someone who comes to the sysadmin and says, hey, I need this change across all of our servers. And the sysadmin says, well, when do you need that by? Oh, I need it yesterday. We've all had it happen. And it turns out that at Facebook, we move fast enough that this is pretty common. But as it turns out, even if you push code or configs weekly or monthly, this is something that I argue you all want. Because when someone comes to you and requests a change, the faster you can prototype it, the faster you can test it, the faster that you can get it ready for production, the faster you can get back to whatever the hell you were doing before then, which means you as a human being scale better. We wanted a tool where we could change the internal assumptions of that tool and change them really easily. Obviously, if you're going to go pick a tool, you're going to try and pick a tool that maps as well as possible to what your internal environment looks like. However, no tool is perfect. Even if you write it yourself, I assure you it won't be perfect. And at some point, you're going to run into a case where you want to do something that just doesn't quite map to the way the tool works. And we wanted to be able to change any such assumptions without having to fork or rebuild the tool. We wanted to be able to simply change that with plugins or configuration. And finally, we wanted a system where we could add features, something that was extensible, in the same way, without forking, without rebuilding. We just wanted to be able to add whatever feature that no one had thought about that we ended up needing in a simple manner. So to take an example of the kind of flexible workflow we're looking at, imagine that we want a template Etsy syscontrol.conf. And we want to do it in a way that somewhere early on in the run of whatever tool we picked, we could do a bunch of calculations and determine what's most likely the right set of values for everyone at Facebook, and then make this hash available. And then every other engineer who has access to the things that run on that system can simply change that hash. They can add values, they can remove values, they can munge values. And then at the very end, we take the resulting data structure and we spit it out as a syscontrol.conf. That's the kind of workflow we're looking for. So with these three needs in mind, it was time to pick a tool. And we looked at all sorts of tools, proprietary, open source, building ourselves. And we narrowed it down to 3 tools to do a large head-to-head test with: Spine, Puppet, and Chef. And we did that big head-to-head test, and at the end of the day, we picked Chef. And I'm not going to stand up here and tell you that Chef is the only tool or even the best tool. Every tool has its place. But what I do want to do is show you why or how we map those needs to this tool and made sure that this was the right tool for us given what we needed. And the easiest way that I can think to do that is with a problem we faced with Chef as opposed to something that we liked about Chef off the bat. For us, node.save was a problem. And in order to understand what node.save is, I have to give you just a really brief intro to how Chef works. When you run Chef on a machine, it starts up and it runs a process called ohai. And ohai does introspection. Finds out about the file systems and the networking and the kernel and the users and all of this stuff about an existing system. And it passes that off to Chef. Chef uses this to build what it calls a node object. During the course of the Chef run, more data gets added to this object. And at the end of the Chef run, it calls a save method on this object, which takes the entire thing and shoves it all up to the server. And if you're most companies, what you now have is a free inventory management system, and that is a beautiful, beautiful thing. It's searchable, it gets all indexed, it's great. However, at Facebook, we already have an inventory management system, and so we didn't have a strong need for this. But moreover, we have clusters that get upwards of 15,000 nodes, and we wanted to run Chef at least every 15 minutes. And taking these massive objects and shoving them over the network every 15 minutes from 15,000 servers would have melted our switches. And if it didn't melt our switches, we would have had no bandwidth left over for all those lovely pictures of cats that everyone likes to post on Facebook. So we looked at the standard solutions, and the standard solutions were kind of lame. They involve things like disabling all of the ohai plugins, or most of the ohai plugins, telling ohai, hey, don't tell me about file systems, don't tell me about the networking information. And that sucks. The reality of it is, I'd like that information when I'm making my decisions. Just don't need to send it to the server. So what was there left to do? Well, Adam Jacob, the original author of Chef, and I sat down and we wrote a cookbook. And a cookbook is just a collection of configuration for Chef. And it's called Whitelist Node Adders. And what it does is reopen the Chef node save method, and then deletes everything from that object that's not in a whitelist, where that whitelist is configurable from anywhere in your configuration. Then it calls the original node save, which saves that up to the server. In our case, that meant less than 1 kilobyte per machine sending back to the server, which is something we can obviously handle. The code is, of course, available. Now, I don't want to dig too much into the code, but I did want to put it up on the screen for one reason. 4 lines. I will get out of the way of the code. 4 lines of code that essentially fundamentally alter the core assumptions of this tool. Now, I'm cheating slightly here because the filter function's not on the screen, which is about an extra 25 or so lines. But really, ultimately, what it comes down to is 4 lines of code that fundamentally change this core assumption of the tool. And that, it's hard to argue, is super, super flexible. So I know a couple of you are sitting there squirming in your seat thinking, oh my God, he monkey patched this tool from its config. That's horrible. And you're right. I would not recommend, say, configuring your web server by monkey patching your configuration management system. But to have this hammer when you actually need it is incredibly, incredibly useful. And we've used this to do bug fixes before a release came out, or to backport features for a release that we were not ready to upgrade to. With that said, let's talk a little bit about our desired workflow that we wanted to build now that we had this tool. We wanted to provide an API for anyone, anywhere, and by anyone I mean these service owners, to be able to configure anything they wanted on their local system simply by munging these data structures. Very simple data structures, hashes and arrays. We wanted engineers to not have to know what it is that they're building on top of just because they want to change something. So if I want to move core files, to use the previous example, which happens to be in syscontrol, it doesn't mean I should have to know how to configure every other value that happens to be controlled by syscontrol. We really wanted engineers to be able to make changes without fear of changing things they didn't expect to change. So if you want to change a value on a web server, you shouldn't have to worry about whether or not you're going to break the database servers, and vice versa. Testing had to be easy. If testing is not easy, people don't test, and that's bad. And if you require people to test, and it's still not easy, then what happens is no one ever makes changes, and that's also bad. So testing had to be easy. There's one other thing, and ultimately this is where I think this talk changes from most other configuration management talks you'll see, and there was no name for this concept, so I had to make one up. And I call it idempotent systems, or moving idempotency up the stack. And what do I mean by that? If you think about modern configuration management systems today, Puppet, Chef, whatever, they prefer to manage specific records, a user, a cron job, a syscontrol setting, whatever, just one of those things. And so this leads to a problem. When you don't want to have that thing anymore, if you delete it from your configuration management system, it does not delete it from the world. It becomes stale. Imagine, alternatively, if I could give an entire system, say, all users, or all cron jobs, or all syscontrols, to my configuration management system, and have it manage that entire system as one idempotent entity. In that case, when I remove something from my configuration management system, it magically disappears. Let's look at this in a more visual manner. This is a diff, made up diff, but a diff of a change that you could potentially make. So we had some user and some cron job, and we decided we don't want this anymore. So given current practices, the way you would do this would you add action delete, which is Chef's way of saying, hey, remove this, and then you add this comment at the top. This comment says, delete this code after this and this date. And like, that's lame, right? No one's gonna clean that up. That's just cruft sitting around your environment. That shit sucks, right? No one wants this. Imagine instead if we could have this. Just delete the thing you don't care about anymore and have it go away, magically, automatically. And of course, it doesn't work like that today, so how do we make it work like that? Well, I'm gonna take you back to the example that you are already starting to get sick of because I keep mentioning syscontrol. So in the CF Engine 2 days of Facebook, we had 151 copies of syscontrol.conf, which were impossible to manage or understand. And the reason is because you'd have a web server one and someone would copy it because they needed to make a change for their environment. And they'd change one line, and immediately you have hundreds of lines of config that are now stale. And then someone else would copy it and so on and so forth. So we solved this problem. We wrote FB syscontrol, which is the name of a cookbook. And in attributes, which is the part of a cookbook where you set up sort of default data for your cookbook, we have a bunch of Ruby that looks at the current system and tries to come up with the most sane set of syscontrols for every syscontrol we've ever cared about and puts that in a hash in the node object. The recipes file in a cookbook is where you define what resources you would like to manage and how, and we just say, hey, we're going to manage at syscontrol.conf, and it's going to be managed with this template. And then we have the template. And the template is a simple 3 lines of Ruby. And if you don't read ERB, which is the Ruby templating language, the top 3 lines there, all they do is loop over a hash and print it out in order. Key, space, equals, space, value. You can see the result on the bottom, syscontrol file. And I know you're saying, well, but Phil, that's 3 lines of Ruby, that's not special. And you're right, it's not. But what is special is this. The DBAs come along, they write a 2-line cookbook that assigns 2 variables, and bam, they have more shared memory. They didn't have to ask me. They didn't have to inherit a bunch of syscontrols. They don't even have to understand what syscontrol is. They just need to know what variable to assign a value to, and that's it. When they delete these 2 lines because they decide, you know what, we don't really need that setting anymore, they revert back to the Facebook global defaults. That's really powerful. So how does this help us scale? Well, the DBAs no longer have to understand every syscontrol in the world. They only have to understand the 2 they care about. I don't have to understand every possible combination of every syscontrol at every server all across Facebook. So I can do my job more effectively, and they can do their job more effectively, and both of us now scale better as people. And because of that, We scale, because of that, we get a lot of scale. And also, um, we're only expressing delta configuration. We're only expressing how the database servers diverge from normal servers, meaning that we have less config to manage, period. Few other very quick examples. We have a variable that says whether or not you want v6. It enables it and gives you an address or removes the modules. We have Boolean functions that'll tell you where you are, what stats about your cluster, in this case, whether or not you're in one of our layer 3 clusters. And one of my favorites, our cron job API, which is a hash. You simply add an entry into a hash, you get a cron job. Delete these 5 lines, cron job goes away. Another example is DSR, which stands for direct server return or direct server response, depending on which vendor you talk to. And some of you may have run into this if you've dealt with large web traffic. And it refers to the concept of having a VIP where traffic comes in through a load balancer, gets routed to a backend, and then that backend responds directly to the internet, to the client that made the request. And this can save you a lot of money on load balancers, but it requires a fair amount of routing and network considerations on your backends. And as it turns out, the routing and network considerations there can change pretty significantly based on whether you're layer 2 adjacent to your load balancer, whether you're v4 or v6, what version of the kernel you're running, all sorts of stuff. And it got to the point where in the CF Engine 2 days, rolling out of a DSR VIP across Facebook involved creating tens of files and a lot of lines of CF Engine code. And that just sucks because you had to understand all of these complicated things that you probably shouldn't have to understand to write an app. And so we changed that. There's a function, add DSR VIP. You give it an IP address, it'll figure out all of the things that you need based on the network you're in, the cluster you're in, everything else, and just do the right things. People can express the configuration they want. I don't have to know every configuration in the world. I just have to maintain the code that can figure out how to do it. So let's take a quick look at our Chef infrastructure at Facebook. Small disclaimer, we use both open source Chef and private Chef. We paid for private Chef mostly to get early access to features and a couple of the management tools. But it is very important to us that we can work with the community, leverage what they do, and have them leverage what we do. So we will always run open source Chef in production. So some of our clusters run open source Chef, others run private Chef, as a way to guarantee the community that open source Chef will always scale to a Facebook-sized cluster. So we have a bunch of things we do a bit differently in order to ensure the scale that we have. We'd like to treat Chef servers as stateless, as commodity hardware. So we don't use search, which wouldn't make sense anyway because we don't save any data back to the server, as I mentioned earlier, so there is nothing to search. But even if we did, search wouldn't scale for us. Data bags are arbitrary key values you can store on a Chef server. We don't do that either. That's data on the Chef server we'd have to sync, and we don't want to. We have separate failure domains at Facebook. Every cluster is unique and independent and shouldn't depend on any other cluster. So if I have an arbitrary failure in one cluster, it should not affect any other clusters. And finally, we use what Private Chef calls the tiered model, meaning there's stateful front-end Chef servers that run the API endpoints that clients connect to, and that can scale linearly. And then there's a backend that runs the database, which is the quote-unquote stateful part of it, but we try and make that stateless as well. So let's look at this in practice. At a global level, we have some code. Someone writes a cookbook or a role, and they would like to commit it. And all code at Facebook has to go through a code review. So you get your code review, and then you do lint. Lint is the code review system automatically lints. So it runs food critic for chef correctness and Taylor for Ruby style. And then once you've committed to the SVN repo, it's immediately available to all clusters globally. So let's zoom into one of those clusters. In any one of our clusters, we have 2 Chef backends. They are active-passive. The load balancer picks a specific one that's currently active. And then we have 3 fully stateful front ends. Those backends run a piece of software called grocery delivery, which is open source that we wrote. And what it does is it checks out subversion. It keeps a checkout. Every minute it's running cron. It does an SVN up and looks at the difference between the last time it woke up and now, does an SVN diff of them, or a git diff if you're running git, and then looks for any cookbooks and roles that have changed and uploads them, any that have added, uploads, any that have been removed, it deletes. In this way, if one backend falls off the network for a little while, when it comes back, it keeps itself up to date. If we reimage it, it'll figure itself out. In this way, we keep all clusters in sync as well as all backends within a cluster in sync. As I said, this enables us to treat our Chef servers as a little bit more stateless. A couple of implementation details here. Some of you may be thinking now, well, Phil, if you don't save node data, then you don't have any information to make decisions. Like, how do you make decisions on how to configure a specific host? And you're right, I've left something out. At Facebook, we have two systems of record. One will tell you information about a specific host in its network and its cluster, and another one is a grouping system. It puts hosts in groups, and those groups in groups. And we wrote an OHI plugin that queries both of these systems and gets all of the data for the current host and provides that as part of the node object so that all of the Chef code can just simply make decisions based on that data. The final piece is run lists. A run list is the list of cookbooks that you're going to run on a given machine, and this is typically controlled by a Chef server. And again, we didn't want to have any persistent data on the Chef server, so we make each client request its run list by itself. So each client has a file on disk that specifies its run list, and it requests that from the server each time. And in this way, we can reimage any Chef server anywhere, and it just works. On the client, we wrote a report handler that feeds all sorts of data into monitoring, last exception, time since last run, that sort of stuff. We can globally monitor the state of Chef runs. And on the server, we wrote something called Chef Server Stats, which is open sourced. And what it does is flavor agnostically look for any monitoring data. So it works on private Chef and open source Chef, 10 and 11. It'll find anything running that's related to the Chef server, pull as many stats and health bits out of it, build one big JSON object, and spit it out. So you can pipe it into any monitoring system out there. And it's on our GitHub repo. Which leads me to the pretty part of the presentation. We've discussed all of the ideas and philosophies behind what we did. And of course, what everyone usually wants to see when they see a Facebook presentation is pretty graphs. So before I can answer the question is, does it scale to Facebook? I have to sort of define what that means. At Facebook, we have clusters that are 10 plus thousand nodes, 10 to 15,000 nodes. They're pretty big. And we run Chef every 15 minutes on every machine anywhere in Facebook. And with a 14-minute splay, meaning some random amount of sleep, so that they're distributed over that 15-minute period. And then grocery delivery runs every minute, which means we have roughly the Domino's pizza delivery guarantee of all of your changes and all of production in 30 minutes or less. We also have lots of clusters. And what do I mean by lots of clusters? Well, I can't give you an exact number because my lawyers would get very angry. But what I can tell you is that we have multiple clusters in a data center, multiple data centers in a region, and multiple regions. So if you do a little bit of math, you can come up with some good guesses. So when open source Chef 11 came out in December of last year, we were pretty early on in our migration. But we'd been working really hard with Opscode, the company behind Chef, to get their rewrite of the Chef server into open source. And what they had done was they had rewritten the Ruby API endpoint onto Erlang and moved the backend from Couch onto Postgres. And it was supposed to scale much, much better. And so we had that in private Chef. It landed in open source Chef. And I thought, well, what if I throw 2 clusters at it? And so I did. You can see that on the right-hand side, no, left-hand side, the red line is CPU idle of the active backend, and it's running at about 80%. And there's 9,000 nodes. As I said, we were early on in our migration, so not all of the cluster was talking to Chef yet. And so I deleted all the nodes. It took 2 tries because there was a bug in my script. And then I reconfigured 2 load balancers to point at the same Chef infrastructure. And what you can see here is that as all of these 17,000 nodes register all at once, CPU idle drops only to 67% to register 17,000 nodes. And then as cookbooks sync and other things happen, there's another brief dip there down to 63%. And then it comes back up to around 80%. And The graph looks like there's a peak there, only because it's zoomed out. It actually levels off at about 80%. So 80% for 17,000 nodes is pretty awesome. But let's go back in time further. In Private Chef, they got early access to this rewrite. And the way this happened was Opscode took the 3 heaviest used endpoints from their Ruby server and rewrote them in Erlang and delivered a build of Private Chef that had just those 3 endpoints moved over, and the data related moved over to Postgres, and everything else was still in Ruby plus Couch. And that's what we were using for our initial rollout. And so when we started our rollout, we did 1 machine, and then 5 machines, and then 10 machines. And once we got comfortable with the process, we settled on a cadence of about 600 machines in a go. And what I noticed was every time I added 600 machines in this cluster to Chef, I lost more CPU idle on the back end than the previous time. And that did not make me feel very comfortable. So when I got to 50% CPU idle, I decided, you know what, I'm not comfortable going any further. And at this point, I only had 4,000 nodes on Chef. And this was clearly not going to meet our scaling needs. So I called Adam at Opscode again, and I said, hey, this isn't working. And I gave him all the data, and he said, I'll call you back. He had a meeting with his developers, and he called me back, and he said, and I quote, we can probably put more thrust on that pig, which, if you've ever met Adam, is the kind of thing he says. But he said, rather than fix the existing software, we've been working on this rewrite forever, and it's pretty much done. How about you just move to that? And I said, oh, the Erlang rewrite. And he said, yes. And I said, well, how's that going for you in Hosted Chef, which is their software as a service offering? And I said, no, we're not running it yet. And I said, well, how have your other customers found it? And he said, nobody's seen this code yet. Like, we're just about to package it up and hand it off to you. And I thought for a minute, that's scary. But I said, fuck it, we're Facebook, let's do it. So we did. And what you see here is we were running at 50% CPU idle again, and the only new line on this graph is the green line, which is the standby backend CPU idle, which is not doing anything, which is why it's very high. And you can see we start the upgrade about halfway through the graph here, and once the nodes finish registering, we're at 85% CPU idle. And Adam and I looked at this and we thought, that can't be right. Something's wrong. Chef runs aren't happening. So we made a change and we watched it propagate. Well, okay, chef runs are happening. Monitoring must be broken. So we spent forever trying to dig into monitoring and make sure that this was happy. And it turns out it was totally right. The new software was using less CPU idle, managing 4,000 nodes, than the old software was running, managing 0 nodes. So good improvement. So then it was like, great, let's throw more nodes at it. So again, the graph zoomed out here. There's actually a step function there of about 600 nodes at a time. But we ramped up to the rest of the web servers in that cluster, which was 7,000. And as we did, CPU idle only dipped down to 72%. And it's worth noting here that Private Chef, because of its role-based access control model that doesn't exist in open source Chef, client registration is more expensive than in open source Chef. So this is the most expensive part for Private Chef. And it only dipped down to 72% CPU idle. After the nodes are registered, again, there's an additional dip there as cookbooks are synced down to about 70%, and then it settles in at around 80% CPU idle, with those nodes checking in every 15 minutes. So pretty awesome. Quick note about testing, and then I'll summarize. I'm probably going to run 2 or 3 minutes over here. Obviously, different code needs to be tested at different levels. But after you do all of that standard testing, one thing we firmly believe is that unless you see what your code's going to do on a production machine, you have no idea what it's going to do when it hits production. So we test in production. We wrote something called Chef Test, which utilizes a function of Private Chef. It's the only place where we actually depend on Private Chef is in our testing infrastructure. A feature of Private Chef called multi-tenancy. And what it does is allow you to create virtual Chef servers on an existing Chef infrastructure. And they're called organizations, or orgs. So when you run Chef Test, it's just a wrapper. You run Chef Test init, it creates you a user and org. And then when you run tests, what it does is take your local checkout of your configs, upload them to this virtual Chef server, log into the machine in production you want to test on, and change its configuration to point to your virtual Chef instance for 1 hour. And during this time, you can re-upload your code as many times as you want, run Chef as many times as you want, until you're happy with the results. And then you can send that code off for code review. And at the end of 1 hour, it automatically reverts back to production, so you don't get bit rot anywhere in production. So some lessons that we learned. We learned that idempotent systems are vastly better for idempotent records, especially at large heterogeneous scale. Delegating delta config definitely leads to easier heterogeneity. We learned that full programming languages are far better than restrictive DSLs. Having things like loops and if statements, really useful. Probably the single most important thing, if I had to point to one thing I would like everyone to remember, it would be this one. Scale is more than just the number of clients. Whether you have 5 machines or 500,000 machines or 5 million machines doesn't matter. At the end of the day, the way you scale the people who manage those systems is far, far more important. People are a much more expensive resource. Easy abstractions are really critical, and testing in production is useful. So, in summary, what about those 4 questions that we asked ourselves in the beginning? How many homogeneous systems can you maintain? Well, in our test, the first test I showed, we had 17,000 nodes, give or take, running on a Chef infrastructure that had CPU idle of 80-ish%, which means we had a lot of room to grow, and that was heterogeneous. Homogeneous is less computationally intense, giving us our first 2 answers. We can do way over 17,000 homogeneous systems and over 17,000 heterogeneous systems. How many people are needed? Well, my team is 4 people. And finally, can you delegate delta configuration? I believe we showed that we can. With that, I would like to thank some people at OpsCode, namely Adam Jacob and Chris Brown and Steve Dana and the Chef and Bifrost teams, Andrew Crump for writing Food Critic, which is awesome, and everyone that I have or do work with, Aaron, Bethany, David, Casey, Larry, Pedro, and Tyler. That's all I got.